All right, let's get started. Good morning or good afternoon, depending on where you are. Welcome to this KCI webinar on the future of biosolids, navigating the perfect storm. My name is Mehmet Boz, and I'm a vice president with KCI Technologies, and I'll be today's moderator. Our topic today is biosolids. Today's topic will provide an overview of the wastewater treatment processes that generate sludge and the most common means of sludge handling and disposal, along with the emerging issues in the near term. Our presenter today is Wes Halsey, our South Atlantic Water Wastewater Regional Practice Leader. Wes is a registered professional geologist in South Carolina, North Carolina, and in Georgia. He has a long history of working with biosolids, including transport and land application. Wes joined KCI through KCI's acquisition of HMW in 2020. Keep in mind that you can ask questions during the presentation. If you have any questions, please use the Q&A button down below to ask them. We may try to answer your questions during the webinar, but we will likely keep questions to the end of the presentation, and we will try and provide responses during the brief Q&A session at the end. With that, I'll turn it over to Wes.
Thank you, Mehmet. Good afternoon, everyone within KCI, and I would like to particularly offer a warm welcome to our guest. Happy Earth Day. Today is Earth Day, so it's appropriate that we're doing a presentation talking about something that is applied to the environment. I'm here to talk about a subject that everyone enjoys hearing about over lunch: sludge, otherwise known as biosolids. But before I get into the presentation, I wanted to offer a quick story regarding our biosolids management company, Halsey Environmental and LHR Farms. Kind of our claim to fame is that we enabled the 1996 Atlanta Olympics to remain open, or should I say certain venues, because they did not adequately prepare for sewage hauling and disposal. And so that's kind of our claim to fame. The LHR Farms offered land application services to the Atlanta Olympics, and that really launched our business back in 1996. I wanted to offer some quick acknowledgments for use of videos. The Rural Community Assistance Program for offering 2 videos on secondary treatment and also sludge handling and dewatering. Also, the company Wessick out of Canada for providing a video for land application, and also Humdinger Equipment, which is a manufacturer representative in the US for TANA Corporation. And I would also like to acknowledge Rebecca West, who contributed some of the information in some of the slides. Rebecca is a WEF, or Water Environment Federation Fellow, and also past president of the Water Environment Federation. Next slide, please. Biosolids, what are they? Or sludge? The term biosolids was coined by US EPA in the early 1990s to provide a more palatable name for wastewater sewage sludge. Biosolids are the nutrient-rich organic material that are generated within a domestic treatment process or a wastewater treatment facility, otherwise known as a publicly owned treatment works. Through biosolids management, solid residue from wastewater is processed to reduce or eliminate pathogens, minimize odors, and also treated and processed to form a safe, beneficial agricultural product or fertilizer that farmers can utilize on their fields. Biosolids or sewage sludge is carefully monitored and must be used in accordance with the appropriate regulatory requirements. Next slide. Let's just do a quick review of what the regulatory framework for the generation, treatment, and disposal of biosolids. The Federal Clean Water Act of 1972 provides the overall regulatory framework for wastewater treatment and discharge to the waters of the U.S. Under the Clean Water Act, you have the National Pollution Discharge Elimination System, otherwise referred to as the NPDES permitting program. So every wastewater treatment system that discharges to the waters of the U.S. is required to have an NPDES permit. The NPDES permit typically provides terms and conditions related to the handling, treatment, and disposal of sewage sludge. In 1991, EPA promulgated 40 CFR 258, which provided the design criteria for municipal solid waste landfills, where some sludges are disposed. In 1993, EPA promulgated 40 CFR 503, which provided the criteria for land application of sewage sludge, and also sewage sludge that is fired within an incinerator. And of course, the two regulatory agencies that manage the permit and compliance for wastewater treatment and also biosolids disposal, the Environmental Protection Agency, and most regulatory programs are delegated to the respective state environmental agencies, which are tasked with issuing the permits and compliance with the applicable federal and state environmental laws. Next slide. So what are biosolids? Most people have a misconception of biosolids as being just piles and piles of fecal material. Well, biosolids or sewage sludge is not really fecal material. They're predominantly made up of the cellular mass of wastewater treatment organisms. So when you see sewage sludge being land applied to farmland or sewage sludge being disposed of in the landfill, it's basically a mass of microorganisms that have been wasted from a treatment process. Sewage sludge can also include grit, sand and silt, organic forms of nitrogen, as well as ammonia, nitrogen, and phosphorus. Sludge can contain metals that have been removed from the wastewater treatment process, as well as some persistent organic chemicals that are not destroyed during the treatment process. Sludge can also include some partially digested fat, salts, and grease, and can, if it is not treated, contain pathogens within the waste itself. Next slide. There can be various sources of biosolids other than the publicly owned treatment works. Many folks that are not discharging their sewage to a publicly owned system may have a on-site residential septic system or discharge to a community septic system. Sludges can accumulate within a septic tank, which has to be periodically pumped. Also, industrial wastewater treatment processes or pretreatment systems can generate sludges. Pretreatment systems partially treat their wastewater, process wastewater prior to discharge to the POTW, or in some cases have full treatment processes for direct discharge to the waters of the U.S. Or to the land surface through a spray field. Next slide. But we're going to focus primarily on those domestic sludges generated by an advanced wastewater treatment process at a publicly owned treatment works operated by a municipality or a sewer utility. Pollutants that are typically removed by the wastewater treatment process include suspended solids, which can include various forms of nitrogen, synthetic organic molecules removed from the wastewater, phosphorus, and dissolved phase and suspended solid phase metals. Next slide. For those of you not familiar with the advanced wastewater treatment process, just wanted to provide a quick overview through this graphic. Sewage is typically collected within a centralized wastewater collection system or pipes, either gravity or that are conveyed to large gravity trunk lines or to sewer pump stations and force mains and conveyed to the headworks of a treatment plant. What's included in the headworks? Typically an influent pump station and some type of influent screening stage that removes the coarse solids and trash from the raw sewage waste stream. From the screening stage, wastewater is typically conveyed to a primary treatment stage or primary clarification. From primary clarification is typically conveyed to some type of secondary treatment or secondary aeration, and also secondary clarification, where the sewage sludge is removed from the system through a wasting process, and some of the sludge is returned as what we refer to as RAS, or return activated sludge. The waste sludge is typically conveyed to some type of digester, either aerobic or anaerobic. On the next slide, the Rural Community Assistance Program provides an excellent instructive video on the secondary treatment process that includes aeration and also secondary clarification. If we can move to this next slide in the video.
I'm Bill Hoger with Rural Community Assistance Partnership, and we're at the secondary treatment process in the wastewater treatment plant. In the primary treatment process, we removed material by physical means. In the secondary treatment process, we utilize microorganisms to take the contaminants out of the wastewater. Now, these microorganisms are made up of bacteria and amoebas and protozoan, and they eat the contaminants. So what we do is we give them an environment where they like to grow. We give them a home where they want to live. So the ones that use oxygen, we give them air. And the ones that don't use oxygen, we give them a place where there isn't any air. We circulate them around, keep them in solution, feed them the contaminants in the wastewater, and then we settle them out, bring them back to the front end of the plant and have them do it again. There are safety concerns with the secondary part of the treatment plant. One of them is that in an aeration basin, the water is full of tiny bubbles of air, which makes it a lot less dense. So if somebody fell in, they would not be able to swim because they wouldn't float. So safety concerns are very important with wastewater treatment. So you need to have life jackets and railings and make sure that nobody falls in.
And at this point, we'll move on to the next video that describes the solids handling, thickening, and dewatering process.
I'm Bill Hoger with the Rural Community Assistance Partnership. And in this section, we're going to talk about sludge handling and treatment. In our main wastewater treatment process, we took the contaminants out of the wastewater and concentrated them in the sludge. Now we've got to treat the sludge in order to make it less toxic, to destroy the pathogens, and have less of an impact on the environment. We also want to make it where it's easier to handle. And the processes that we're going to look at, they include thickening, digestion, and dewatering. These processes will take the sludge, recover some of the energy from it that we can use to power our wastewater treatment plant, and also turn out a beneficial product that can be used for soil conditioning. This is the sludge thickening process. It's the first step in the solids handling processes, and it's very similar to clarifiers that we looked at before, where we slow the water down and allow the solids to settle out. But the special feature of thickening is that we're taking our solids concentrations from about 0.5% all the way up to 6% solids. The reason we do that is so that we have less energy to pump the solids and so that we have a better treatment in the remainder of the solids handling processes. In the gravity thickener, we use gravity to settle the sludge out and make it thicker so it was easier to treat in the rest of the solids handling facilities. In this facility, it's a dissolved air flotation thickener, or a DAFT, and in it we take and dissolve air in the sludge under pressure, then we release that pressure and the sludge floats to the top. We end up with about a 5% solids blanket on the top, which we scrape off and send to our solids handling facilities for digestion. We're in the pump gallery for the sludge digesters. We've thickened the sludge in the sludge thickeners and we've sent it over here to the digesters. In the digesters, we heat the sludge up and the microorganisms start to break it down, get rid of some of the volatile compounds, make it to where it won't degrade any further. In that process, it also destroys some of the pathogens. When we're finished, the sludge is turned into a useful product. But during that process, we also generate some methane. That methane gas we can use to run generators, and those generators power part of our wastewater treatment plant. They also generate waste heat, which we use to heat up the digestion process. So it's a nice circle. We use a whole lot of the energy that's stored inside that sludge to make our process cheaper to operate. This is the digested sludge. After we've used microorganisms and heat to destroy the pathogens and reduce the material that might degrade further and cause odor problems. But there's still a lot of water left in this sludge, so we're going to have to do some dewatering process to get rid of the water, make it easier to handle, cheaper to transport, and so that we can land apply it as a soil conditioner. These are centrifuges behind me, and it's one way to get the water out of the sludge. You can also use a belt filter press or some other kind of filter to get the water out. The centrifuges spin the sludge around just like your washing machine and pull the water away from the sludge, and you're ended up with a cake that's easy to truck away and to land apply.
Okay, next slide. And before we go into some of the issues, I wanted to summarize what two of the most common means of biosolids or sewage sludge disposal. The most common is, as we mentioned, land application or the beneficial reuse of sludge on agricultural land. You're basically utilizing the sludge as a fertilizer or soil amendment. And we generally have two different classes of sludge. Probably the most common that is land applied is a Class B sludge, which has a fecal coliform count of less than 2 million MPN, that refers to most probable number per gram, or 2 million colony forming units, or CFU, per gram of total solids. So the utility has to treat the sludge through various processes to reduce the total fecal coliform count in order to land apply a Class B sludge. The farmland that is typically land applied to are non-public contact sites. There are also significant harvesting and grazing restrictions associated with fields that receive Class B biosolids, and also significant restrictions for food crops that are harvested on fields where Class B sludge is land applied. A less common quality of sludge is a Class A sludge, where the fecal coliform count has been reduced to less than 1,000 mpm per gram, and also provided treatment for reduction and testing of enteric viruses, and also the helminth ova, which is basically a parasitic organism. Class A sludges are typically suitable for distribution to the public in bags or in bulk, and for land application on public contact sites such as parks. And there are no harvesting or grazing restrictions associated with Class A sludge. Class A sludges typically require a significantly higher level of treatment within the wastewater treatment process. Next slide. This video provided by Wessex out of Canada, with their permission, provides a great depiction of the land application process. And this is probably the most common means that liquid biosolids are land applied. Typically, you have a tractor pulling some type of trailer or injection vehicle, such as this. This injection vehicle has an umbilical which extends back to a vacuum pump truck or vacuum tanker, which pumps the sludge through the umbilical, where the biosolids can be distributed evenly over the land surface. Again, this video is depicting land application of a liquid sludge that would still be pumpable somewhere in the 2 to 5% total solid range, which means that this sludge is still predominantly water, so 95+% water. So the tankers that you see are hauling predominantly water, somewhere between 2 to 5% solids or sludge. Next video, please. Or next slide. The second most common means for biosolids disposal is a disposal at a landfill. Not all landfills can receive biosolids, only lined landfills designed in accordance to 40 CFR 258, commonly referred to as a Subtitle D landfill. The landfill operators are typically required to obtain some type of waste manifest from the generator or from the utility, and the utility must demonstrate that their sludges have been dewatered or dried where it meets the paint filter test. What does the paint filter mean? That means it just can't be dripping as it rolls into the landfill. Also, the sludges typically have to have some type of annual TCLP testing to determine its characteristic of hazardous waste, to see if it's a characteristically hazardous waste. If it is, it's not suitable for disposal in a Subtitle D landfill. So only non-hazardous sludges can be landfill. And sludges are typically not utilized by the landfill operators as daily cover due to the potential attraction of vectors. Vectors are insects or scavenging birds that can consume and distribute the waste material. Next slide. Okay, this video that we're going to be viewing is provided at the permission of Humdinger Equipment, and it provides a great depiction of sewage sludge being disposed and compacted within a municipal solid waste landfill. And I enjoy the music of this video. And you'll see this compactor is spreading and compacting municipal waste. In the next scene, you'll see the spreading and compaction of sewage sludge. And if you notice that the sewage sludge is compacted into layers, typically sandwiched in between the layers of municipal solid waste. One thing I wanted to point out is this layer of sewage sludge typically can have a lower shear strength that can degrade the structural integrity of the landfill, and that's one of the issues that we're going to discuss. The sewage sludge that you see depicted in this video is probably compacted somewhere higher than 20% total solids. So it still contains a lot of water. There's also the potential that the sludge that is disposed in the landfill can be re-wetted by direct precipitation in the landfill or re-wetted when it comes in contact with landfill leachate. Okay, next slide. So that leads us to some of the emerging issues, and really what prompted the planning of this presentation. About 2 years ago, we started receiving calls from a number of our utility clients concerned about the disposal cost at the landfill. Several years ago, utilities were paying anywhere from $35 to $40 a ton tipping fee at the landfill. Today, they're paying anywhere from $70 to $100 per wet ton for tipping fees at landfills. So the landfill costs are escalating significantly. Also, many of you have probably heard by now of the forever chemicals called PFAS, either perfluorinated alkyl substances or polyfluorinated alkyl substances. That is also a major concern and that will potentially affect the future of biosolids disposal. Also want to introduce some of the public perception issues typically associated with sludge, and that's, of course, odors. Land development is also a factor as we have urban and suburban sprawl, particularly with the rapid development in the South. Former agricultural land is being converted into residential subdivisions and forcing utilities to have to transport their sludge further to agricultural fields for land application. And we also see that the US EPA is issuing new requirements for groundwater monitoring and assessing the risk of groundwater quality associated with the land application of sewage sludge. Next slide. Okay, within the landfill, over the last 10 to 20 years, we have seen reported incidents of waste slides within the landfills throughout the US and also throughout the world. Many of those waste slides have been attributable to the presence of compacted sewage sludge within the landfill itself. That layer of sewage sludge has a weaker shear strength that affects the structural integrity of those landfill cells, causing waste slides. Some of the waste slides have even caused fatalities at landfills. Also, I wanted to mention within the past 5 years, or ever since the promulgation of the federal CCR rule, that's coal combustion residual or coal ash rule in 2015, EPA is requiring all coal-fired power plants to dispose of their coal ash within a municipal solid waste landfill. Formerly, coal ash was typically stockpiled in large piles or impoundments at the power plant itself. Massive volumes, millions of tons of coal ash have been excavated and transported to municipal solid waste landfills for disposal over the past few years. The photograph that you see on the left is a side dump trailer that we commonly observed on Interstate 85 heading to a landfill in Georgia. This occurrence has caused the rapid consumption of landfill airspace, competing with other waste streams such as municipal waste and sewage sludge, driving up tipping fees significantly at the landfills. Next slide. Regarding disposal of biosolids within landfills, we've seen several states take action to prohibit disposal of sludge within landfills. Private landfill owner operators are starting to require their sewer utilities to dewater further or dry their sludge or amend their sludge with amendments such as lime or diatomaceous earth to increase the shear strength of the waste going into the landfills. Also, landfill operators are having to modify their sludge disposal practices to enhance the structural integrity of the landfill and the waste itself to prevent or reduce the risk of waste slides. Next slide. Some of the emerging issues in biosolids, as we mentioned before, is the discovery of the forever chemicals within the wastewater or sewage stream, which can end up in sewage sludge. Why are we concerned about PFAS? Well, EPA has determined that PFAS compounds can have human health effects, but we also have discovered that PFAS is present in a number of products that we come in contact with every day. It can be within shampoo, Teflon pans or nonstick cookware, stain-resistant applicants that are sprayed on fabrics and furniture, can be included in paints, pesticides, photographic equipment and materials, and very common within firefighting foams. Next slide. The graphic that we're looking at today is how PFAS can enter the environment. Of course, the products that are produced that contain PFAS can be disposed of in the landfill. And the landfill itself generates leachate leachate is commonly disposed of at a POTW under a industrial pretreatment program. Firefighting foam, if there are fires at industrial facilities where firefighting foam is applied, that foam can enter a sewer collection system to be conveyed to a treatment plant. Airports that utilize firefighting foam, those foams can inadvertently be washed into a sanitary sewer collection system, and in some cases, storm sewer collection systems, and enter the waters of the U.S. Some manufacturing processes have emissions that either through their stacks into the air or to the water through direct discharge. Also, groundwater contamination has occurred from industrial facilities that manufacture PFAS containing compounds, and those compounds have entered the raw water or source water of many drinking water facilities. That PFAS containing compounds can enter the wastewater treatment process through these various mechanisms and ultimately end up contaminating the biosolids themselves. Next slide. Another issue with sludge, and this is not really an emerging issue, this has been an ongoing issue for decades. What is emerging is how former agricultural land is converging with rapid residential development. So subdivisions are being built closer to farmland, where sludge is land applied, and sludge can have odors associated with it. Also, treatment plants are being encroached upon by residential development, and those treatment plants can have some odors associated with their sludge handling process. And certainly landfills are being encroached upon. Landfills where biosolids are disposed of can commonly have some type of odor associated with the operation. Next slide. Why do sludges smell? Well, very commonly sludges can contain mercaptans, which are organic sulfur compounds. Any of you that have natural gas systems or propane gas systems in your household, if you ever have a gas leak, or if you're starting up your pilot lights for water heaters or gas logs, you'll notice a certain smell. Well, that smell is associated with mercaptans that are mixed with natural gas or propane to provide the odor. So an explosive level of gas is avoided, contribute to the odors associated with sewage sludge. Well digested, well treated, and efficient sludge treatment processes typically generate sludges with minimal odors. When a sludge turns anaerobic or anoxic or septic, they can typically have a significant odor associated with that process. Next slide. What sewer utilities need to consider if you dispose of your biosolids within a landfill. You need to know what's in your sludge. Does it contain PFAS or PFOA? Review your existing landfill contracts and how the condition of your sewage sludge in terms of dryness, shear strength, whether or not it contains some of these emerging pollutants. Discuss with the landfill any capacity concerns. Are they taking waste streams such as coal ash that may inhibit or limit the amount of sludge that you can haul to that landfill? You need to understand the issues the landfill is facing regarding any future challenges associated with waste slides or prohibiting the future risk of waste slides. Some private solid waste management companies are even requiring geotechnical testing of their sludge for compressive strength and requiring sludge generators to further dry their sludge or add amendments to their sludge to increase compressive strength. You may want to inquire with your state regulatory agencies if they are requiring additional sludge drying processes before you dispose of your sludge in the landfill, or even in some cases prohibiting sludge disposal within the landfill. If leachate from the landfill is accepted by a wastewater treatment facility for treatment, the sewer utility may want to restructure the contract in case the leachate can no longer be accepted by the POTW because of PFAS concerns. Next slide. What should sewer utilities consider that land apply their biosolids? Again, you need to know what's in your biosolids and develop an ongoing monitoring program to analyze for PFAS compounds. Also, within your industrial pretreatment program, survey your contributing industrial users to ensure that PFAS compounds are not being discharged to your treatment facility. And at some point, you will be developing a forward action plan with regard to PFAS and other emerging contaminants within your industrial pretreatment program. Survey the local fire departments within your service area to learn who is using PFAS-containing firefighting foams that potentially could be discharged to the sanitary sewer system. If leachate from a landfill is accepted by the POTW for treatment, you would want to test the leachate for the presence of PFAS before it goes into the treatment process. And also understand what the next contaminant du jour may be that will impact your biosolids program. Next slide. Facilities that beneficially reuse your biosolids, you want to work with your customers that you distribute biosolids to, or that would be for a Class A biosolid, or your farmers so that they understand any concerns about the occurrence of PFAS and PFOA within your sludge. Also work with organizations like the Water Environment Federation and also the National Association of Clean Water Agencies to advocate for standards, guidance, regulation based on sound science related to human and environmental risk assessment associated with biosolids land application. Work with local universities and the Water Environment Federation to support and fund research to continue the beneficial reuse of biosolids programs, and also develop talking points for your staff and board members that address frequently asked questions regarding PFAS in your biosolids program. Next slide. Here at KCI, we are recommending short-term, intermediate-term, and long-term strategies for sewer utilities to incorporate into their biosolids master planning. keeping in mind that not one size does not fit all in sludge management, from utility to utility, even from treatment plant to treatment plant. However, these short, intermediate, and long-term strategies may need to be considered for most treatment facilities. The objective here is to keep as many disposal options open while utilities implement long-term measures and capital upgrades to sludge handling. Some of those short-term strategies is plan for more efficient sludge dewatering. The drier the sludge, the less water that you're hauling, and that translates into a lower hauling cost, either to a land application site or to the landfill. You want to start analyzing your sludge samples for PFAS and implement testing, geotechnical testing for compressive stress if required by your landfill vendor. Identify sources of PFAS and PFOA that may enter the collection system and end up at the treatment plant and ultimately in your sewage sludge. Establish a public education program to inform the general public about biosolids disposal and also beneficial reuse programs. Some of the intermediate term strategies that we're recommending is implement efficient sludge dewatering improvements. Enhance your pressing, sludge press, belt presses, screw presses, centrifuges, whatever technologies that you're using to improve your overall sludge dewatering, and evaluate the need for sludge amendments to improve compressive strength if you want to continue to dispose of your sludge in the landfills. Start regulating sources of PFAS and PFOA within your industrial pretreatment program. Ultimately, you may consider developing local limitations for PFAS compounds for your industrial users, if feasible. Also, enhance and evaluate sludge digestion processes and consider odor control measures if odor is a persistent problem, either at the treatment plant or within the disposal sites themselves. And plan for sludge drying in the future to further reduce hauling cost and keeping the landfill option open. Some of the long-term strategies that we are recommending sewer utilities to evaluate. Can your sludge process incorporate some type of renewable energy program, such as anaerobic digestion using hydrolysis for generating biogas or providing fuel for some type of cogeneration generating process at your treatment plant. Also, looking forward to some type of thermal treatment or thermal destruction of sludge within incinerators or some type of solid waste gasification process or pyrolysis. Those disposal thermal destruction or thermal oxidation of sludges is something that we're going to see more and more of 5 to 10 years down the road for many biosolids programs. We also have the opinion that as technology changes over the coming years, these renewable energy systems will provide a much greater cost benefit to smaller utilities down the road. Typically today, those are reserved for the large 20 to 30 MGD treatment plants and higher for those to provide cost benefit to the utility.